Welcome back to my lectures on groups, rings and fields. Our next topic is factor groups. The factor groups are groups made of subsets of another group. So let us start with an example to show that how we are going to construct this group. Let us take an example. Let us take an example of C4. C4 is a set with a binary, is a group with a binary operation as addition modulo 4. We'll take another set. Yes, this is just a set. This is a group. This set has got 4 elements: A, B, C, D. Even though S and Z4 are having the same number of elements, we cannot say that S is a group because there is nothing, no structure defined here. We need to have a binary operation with some rules. So our first attempt is to borrow a binary structure or binary operation or group structure from Z4. Okay, here you have a table, a binary operations table 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 1, 2, 3, 2, 3, 0, 3, 0, 1, 0, 1, 2. And there is nothing like that here. We need to construct a table like this. Then only this will become a group. So our objective is to define, build a group structure on these elements based on an already known group structure. One good thing about these two sets are that the number of elements are same. The cardinality of S is equal to the cardinality of Z4. So we can always build a bijective map. For example, we say A is equal to 0, B is equal to 2, C is equal to 1, 2, 3. D is equal to 2. So still we are not yet reached there that this is a group. This is not a group yet. Only thing is you are identifying these elements using a bijective map. In order for us to think about S as a group, we need to build a binary operation. So the binary operation we are going to define is like this: A times B. This is a binary operation we are going to define. Here the binary operation is addition modulo 4. So here the way we are going to define that is this: mu inverse of mu of A plus mu of B. See, mu of A is an element in Z4, so this is an element in a group. Mu of B is also same thing, so you can add. So you get another element here and take the inverse of that, because mu is a bijective map. You can always think about an inverse map. So that is going to be the binary operation on this. Here, for example, this is going to be 0 plus 1, and that is equal to 1, and mu inverse of 1 is B. So A star B here is B. So this star is a binary operation that satisfies all the group rules or group axioms. So with this star, you can say that S star is a group. So our idea is to build a group with the elements as subsets of a group, but we need to still define a binary operation. For that, we are going to use this technique. So let us start building the factor group. So initially what we are going to do is we are going to build the factor group using a homomorphism. Then we'll come back to any subgroups of G, and we'll create another more generalized version of the factor groups. So we are going to define a homomorphism. So let phi be a homomorphism from G to G prime. With the kernel H. I'm going to write an example here. Let us take G is equal to Z and G prime is equal to Z3. Our idea is to split Z into 3 disjoint subset, and that is what we are going to do here using a homomorphism. So our phi is from Z to Z3 defined by phi of n is equal to R, where R is the remainder when n is divided by 3. So the example is going to be like this. Z is equal to 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, minus 5. And C3 is equal to, it is going to be much smaller than this, is equal to 0, 1, 2. So with this definition, 0 goes to 1, 2 goes to 2, 3 goes to 0, 4 goes to 1, 5 goes to 2, minus 1 goes to 1, minus 2 goes to minus 2, minus 3 goes to 0 again. So we have cosets of Z3. Or cosets, see the kernel of phi is equal to, here it is H, and that is equal to 0, 3, 6, 9, etc., minus 3, minus 6. So this is a subgroup of Z. And we have three different cosets here. One is H and one is, I am going to take only the left coset. In this case, left and right cosets are same because C is an abelian group. 3Z. This is H is equal to 3C. This is H. See, 1 is 3C, 1 plus 3C, 2 plus 3C. So that is what we are going to do it here. Here, the way we are going to get this coset is like this. We know that phi inverse of phi of A is a left or right coset of H, and that is equal to either AH or equal to HA. Meaning, these are actually phi inverse of phi A, phi inverse of phi, let us take 1, is going to be 1 plus 3C. So there is a one-to-one correspondence between A and phi inverse of A. And that is phi of A goes to HA, or that is equal to phi inverse of phi of A. This is actually a one-to-one map, because if you, this is a subset of G, and if you take any element from this, so this is a subset of G containing A, but if you take any element of this, this is going to be same. For example, if you take X belongs to AH, and that implies X is equal to AH for some H in H, and that implies phi of X equal to phi of A times phi of H, because phi is a homomorphism, and that is equal to phi of A, because phi of H is equal to the identity of G prime. So that means if A belongs to H, X also belongs to H. So if you take any element from here, this maps goes to the same element. In other words, if you take any, see, phi of A, X is equal to phi of A. So that means AX, AH is equal to HA. XH. Okay, so that's what I'm saying. So this is a one-to-one. This is a one-to-one map or bijective map. Here, this is going to be. I'm going to take some more space here. So this is. So I'm going to take the collection of all the cosets here. The collection of cosets is 3C, 1 plus 3C, and 2 plus 3C. These are subsets of Z. See, Z is divided into subsets, disjoint subsets like this. And our phi of G is just 1, 2, 3. This is our phi of G. This is a subgroup of G prime. So definitely there is a definitely there is a group structure defined here, and this group structure here it is addition modulo 3. So in here phi of G is a subgroup of G, and we have a collection of all the cosets of H. These are subsets of the elements of this set is a subset of G, and this is actually a subgroup, meaning there is a group structure here, and there is a bijective map from goes to here, and that is our mu. So we are actually getting the, say you have a group here and you have a set that has got the same cardinality as this, and there is a bijective map. And the bijective map here is going to be mu of AH is equal to phi of A. This is the bijective map. With this bijective map, we can build a binary operation on the collection of cosets. So what is a, so how do you define it? Like AH times BH, we want to define like that, is equal to mu inverse of mu of AH times mu of BH, and that's what we found in the earlier session. And what is this? This is actually equal to mu inverse of phi of A times phi of B, and that is equal to mu inverse of, this is actually a homomorphism, so we can write it as phi of A. And phi of AB in mu inverse is going to be ABH. So this is the binary operation we are going to define. When you define like this, then it automatically becomes a binary operation on the collection of cosets of H. So what we have done is, we have a bijective map from mu from phi inverse of phi of A such that A belongs to G. These are the collection of cosets to phi of G. We normally write this one as G over N, or G mod H. Well, H is the kernel of phi. Okay, so we are defining a bijective map of mu from this to phi of G by mu of AH is equal to phi of A. So with this, we can define a group binary operation on the collection of cosets of H by G over by AH times BH is equal to ABH. This is a well-defined binary operation on G over H. So the group G over H with this binary operation is called the factor group. And it is called G over H, or factor group. There is another word, quotient group. Quotient group. Both are same. Or we can say G over H or G mod H. So that is how we are going to define the factor group. Now let us review that example of the homomorphism from phi from Z to Z3. And we know that the kernel of phi is equal to 3Z. So, so what is our Z, our factor group Z over 3Z? That is actually equal to 3Z comma 1 plus 3Z comma 2 plus 3Z. And if you draw the multiplication table, 3Z, 1 plus 3Z, 2 plus 3Z, 3Z, 1 plus 3Z, 2 plus 3Z, 3Z, 1 plus 3Z, 2 plus 3Z, 1 plus 3Z, 2 plus 3Z, 3Z, sorry, this is going to be 2 plus 3Z, this is 3Z and 1 plus 3Z. So this is the multiplication table for this factor group. And what we need to note here is this factor group is isomorphic to the phi of C, and that is equal to Z3. And what is Z3? Z3 is Z3 is a group with 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, 1, 2, 2, 0, and this is 0, 1. See, when you fill this multiplication table, we are filling exactly like this, replacing 0 with 3C, 1 with 1 plus 3C, and 2 with 2 plus 3C. So this Z3 behaves exactly like our factor group. Our factor group behaves exactly like this. And that's why we are saying the factor group is isomorphic to Z3. And what is isomorphism here? Isomorphism is 3Z from C3 is going to be like, what is the element of here? It will be A plus 3Z, and that is going to be phi of A. And that is exactly what is happening here. one more thing we want to note is that if you are building the factor group using a homomorphism G to G prime with the kernel H, then G over H is isomorphic to phi of G. There in the earlier example, phi was from Z to Z3 with kernel Z3Z. Then we found that the factor group or quotient group Z over 3Z is isomorphic to phi of C, and that is again Z3. And this is this isomorphism is our mu. So this is a very important result. G over, if you are building the isomorphism, if you are building the factor group using homomorphism, this is always true. Now let us consider building the factor group without a homomorphism. So why we need the homomorphism there? Because we need a subgroup of G, and that is the kernel of the homomorphism. G from G prime with kernel H. Then we constructed the factor group G over H. But if you have already a subgroup here, let us say any other subgroup, let's say H1, which is not related to any of the homomorphism, can we still form a factor group? Or if we can find a factor group, what are the types of conditions we want to impose on this subgroup? And that's what we are looking at. So once we have a subgroup here like this, or let us make it as K, it is a general subgroup, not related to any of this phi. What is the definition of this factor group? What is the definition? It should be the factor group A plus K or AK. Let's take it as AK. AK times BK should be equal to ABK. This is the definition of the binary operation. So if you want this binary operation to be valid, what is the condition we need to impose on this K? K is not related to any of this homomorphism. If it's a homomorphism, you know that kernel phi is a normal subgroup of this. So our question is that if K is a normal subgroup of G without mentioning any homomorphism, can we construct a factor group? And the answer is yes, and that is the next theorem. Let G be a group, or let H be a subgroup of G. Then the binary operation on the collection of cosets of H defined by A plus H or AH times BH is equal to ABH is valid if and only if H is a normal subgroup. H is a normal subgroup of G. And that is what we are going to prove. If H is a normal subgroup of G, then we can always build a factor group. So what we need to prove is A times H times BH is equal to ABH if and only if H is equal to HA. And this is the definition of normal subgroup. So let us start from here. So let X belongs to H, or let us assume that H comma B times BH is equal to ABH. Sorry, ABH. ABH is a valid binary operation on the set of cosets or collection of cosets. Cosets of H. Now we need to prove that H equal to HA. So let us take one element, X belongs to AH, and we are going to show that X is an element of HA. Then we are continuing the argument the other way, then we'll say that HA is a subgroup of AH, and hence AH is equal to HA. That is the plan. So this means what does this mean? This means there exists an H in H such that X is equal to AH. Now let us assume that this is a valid binary operation. So what does that mean? X times H times A inverse H is equal to X A inverse H. Because A inverse is another element of G. We also have, see, X belongs to H is also, that implies XH is equal to AH. These are same because X is an element of this. So we have this one, and we will also have AH times A inverse of H is equal to A times A inverse of H, and that is E times H, and that is equal to H. But these two are equal, and these are same. That means this and this are same. So X A inverse H is equal to H. And what does that mean? X A inverse is equal to H for some H in H. And that means X A inverse times A is equal to H times A. And that is equal to X is equal to HA. And that implies X belongs to HA. And that implies AH is a subset of HA. And similarly, with the same argument, HA is a subset of AH. And that implies AH is equal to HA. Now let us assume that AH is equal to HA. we want to prove that this is a valid binary operation. We want to prove that, show that AH times BH is equal to ABH. So how do you do that? Take a general element here, take another general element here, and see that that is a general element of this. So let X belongs to AH and B belongs to BH. Sorry, not B. Y belongs to BH. And this implies X is equal to AH1 and Y is equal to BH2. So, and that implies XY is equal to AH1 times BH2, and that is equal to, we combine these two together. This is equal to AH3 BH2 because H1B is equal to B1H, BH2, H2B, H3B because of this. So that means not like this. This is going to be H1B can be written as A BH3 H2. This is because of this, and that implies AB of H, where H is equal to H2 H3, and that means XY belongs to AB. See, X is a general element of this, Y is a general element of this. We want to show that XY is a general element of this, and that's what we want. So what we have done so far is, if H is a subgroup of G, then the following binary operation on the cosets of, cosets means it could be either our left or right coset, but we are going to impose a condition on H, so this is going to be a coset. Cosets on the following binary operation, cosets of H is valid if and only if and only if H is normal. And the binary operation is A times H times B times H is equal to ABH. This operation is on the cosets of H, and H is normal. So it could be either left or right cosets. So this is valid only if H is normal. That is what we proved. Our objective is to create a factor group, just like we did using homomorphism. Instead of the kernel of the homomorphism, we have a normal subgroup here. So our set, the base set, the factor set is G over H is actually A plus H for all A in T. This is the collection of all. This is the collection of all, or instead of A plus H, because we are using AH, This is a collection of all left cosets, left or right cosets. And this is the definition of binary operation. So we have a binary operation and we have a set. Now we need to prove that this is a group. What are the things we need to prove? Binary operation is closed, which is clear because AB belongs to G. So AH times BH is equal to ABH, which belongs to G over H. So for any two elements, if you take the product is also in here. So a binary operation is closed. Identity. The identity of G over H is H because AH times H is actually EH, is equal to AEH, and that is equal to AH. EH and H are same. So the identity of the factor group is H. Now we need to find out for every element in here there is an inverse. So inverse X is for A belongs to G, the inverse of AH is A inverse H because AH times A inverse H is equal to A times A inverse H, and that is equal to H. And this is the identity. So all the group axioms, group rules, group properties are satisfied. That means G over H is a group under the operation H times BH is equal to ABH. And this group is called factor groups. We already defined factor groups using homomorphism, but this is more generalized one. In homomorphism, this H is the kernel of the homomorphism. But here it is any normal subgroup. So we call factor group or quotient group. Or we'll say G over H or G mod H. Let us do a computational problem on the factor group. Find the order of Z2 cross S3 over the subgroup generated by 1 comma sigma 1. So before we get into solving this problem, if H is a subgroup of G, normal subgroup of G, then the order of G over H is equal to the order of G by order of H. This is because this is the number of cosets of H. The number of cosets is actually the order of G by order of H, and that is what this one is. So we need to find out the order of this and the order of this. And I have done a partial multiplication table of S3. We don't need the other part, so I don't want to fill it. You have mu1, mu2 and mu3, because we are going to see only the subgroup generated by sigma 1, and sigma 1 is generated in this area. So here the order of Z2, what is Z2 again? Z2 is equal to 0, 1. So Z2 cross S3 will have 0, the element from S3, like either sigma 0, sigma 1 or dash dash mu 3, and 1 comma sigma 0 dash dash mu 3. There are, how many elements are here? There are 6 here, and there is 2. There are 6 permutation. There are 6 permutations in S3, and there are 2 elements. So the order of C2 comma S3 is equal to 2 times 6, and that is 12. And we need to find out the order of this. The order of 1 comma sigma 1 is going to be, see, sigma 1 is generated by, so the subgroup generated by sigma 1 is equal to sigma 0, sigma 1 and sigma 2. So 1 comma sigma 1 means this will be and it will be 0, sigma 0, sigma 1, sigma 2, then 1, sigma 0, sigma 1, sigma 2. So this is going to be uh, 6. Okay, so 6 C2 cross S3 over the subgroup generated 1 comma sigma 1, the order of this is going to be 12 by 6, and that is equal to 2. We'll do one more problem. Show that AN is normal in Sn and Sn, the factor group Sn over An is isomorphic to Z2. What are Ans? Sorry, first of all, let us start with Sn is the group of all permutations on n elements. An is the group of all even permutation on n elements. Sn is equal to An union the collection of all odd permutations. And we know that the order of Sn is equal to n factorial and order of An is equal to n factorial by 2. So, the order of the collection of odd permutation is also is equal to n factorial by 2. So definitely let sigma belongs to Sn. So that means sigma belongs to either An or sigma belongs to An complement, because this is the collection of all odd permutation. This is not a group. This is a group. So when sigma belongs to An, then sigma An is equal to An. Or when sigma belongs to An complement, then sigma An is equal to sigma N will be equal to, so that is the whole of Sn. And here there is, here see, if sigma N, and that is also equal to N sigma, and here also this is equal to N sigma, because if you compose an even permutation with another even permutation, it's going to be an even permutation. When you compose an odd permutation with an even permutation, it's an even permutation. So because of this implies sigma An is equal to An sigma, and that implies An is normal. And because An is normal, we can define the vector group of Sn over An. And the order of this one is going to be Sn by An, and that is equal to n factorial by n factorial by 2, and that is equal to 2. So this is a group of order 2. So Sn by An, Sn over An is a group of order 2. Any group of order 2 must be isomorphic to Z2, because there are only one way of expressing. See, this is 0, this is 1, 1, and this has to be 0. Otherwise, this will not be a group. So there is only one way of filling up the multiplication table for order 2. So every group of order 2 is isomorphic to Z2. Since every group of order is isomorphic to Z2, Sn over An is isomorphic to, and that's what we want to prove.